Hello everyone, and welcome to Lecture 8 of our Probability Theory course. Today we're going to explore a fundamental concept in statistics and probability, the dispersion of a discrete random variable. In simple terms, we'll learn how to measure the spread or variability of random outcomes. This is one of the most important topics in the entire course because understanding variability is essential in virtually every field, from finance and economics to engineering and the natural sciences. Let me briefly outline what we'll cover today. We'll start with a quick review of mathematical expectation, which we studied in the previous lecture. Then we'll ask a critical question: why is expectation alone not sufficient to describe a random variable? This will lead us to the definition of variance or dispersion. We'll look at two different formulas for calculating variance, examine its key properties, and introduce standard deviation. We'll work through two detailed examples, one calculating variance step by step, and another comparing two distributions with the same mean but different spreads. Finally, we'll discuss the interpretation of variance in real-world applications. So let's get started. Let's begin with a brief review of mathematical expectation, which we covered in Lecture 7. The expectation, or mean, of a discrete random variable x is denoted by e of x and is calculated as the sum of each possible value multiplied by its corresponding probability. In mathematical notation, e of x equals the sum over all I of x sub I times p sub I, where p sub I is the probability that x equals x sub I. The expectation represents the long-run average value of x if we were to repeat the experiment many times. For example, consider our defective items problem where we randomly select 3 items and each has a defect probability of 0.1. The expected number of defective items is 0.3. This means that if we repeatedly took samples of 3 items, on average we would find 0.3 defective items per sample. But now here's the crucial question. Does the expectation tell us everything we need to know about the random variable? The answer is absolutely not. While expectation gives us the center of the distribution, it tells us nothing about how spread out or how variable the values are. This is why we need a measure of dispersion. To truly understand why dispersion matters, let me show you a compelling example. Consider two random variables, x and y. Both have exactly the same expected value of 0. Variable x takes values -10, 0, and +10, each with probability 1/3. Variable y takes values -1, 0, and +1, also each with probability 1/3. Now both have expectation 0, but they are fundamentally different. For x, the values are far from the mean. -10 and +10 are very far away from 0. For y, the values are very close to the mean. -1 and +1 are just 1 unit away. If these represented investment returns, for example, x would be a high-risk investment with huge potential gains and losses, while y would be a low-risk investment with small fluctuations. The expectation alone of 0 would suggest they are identical, but clearly they are not. This is why we need a numerical measure that captures this difference in spread. We call this measure dispersion or variance. It tells us how much the values deviate from the mean on average. Without this measure, we would have an incomplete picture of the random variable's behavior. Now let's formally define variance. Variance, also called dispersion, is a measure of the average squared deviation of the values from their mean. It's denoted in several ways. You might see d of x, var of x, or the Greek letter sigma squared. The formal definition is variance equals the expected value of the square of the difference between x and its mean. In other words, we take each possible value, subtract the mean, square this difference, and then take the weighted average using the probabilities. For a discrete random variable, the variance is the sum over all values of x sub I minus mu, all squared, multiplied by the probability of that value. Let me explain why we square the deviations. If we simply average the deviations without squaring, the positive and negative deviations would cancel each other out, and we would always get 0. By squaring, we make all deviations positive, and we also give more weight to larger deviations. This is why squaring is essential. The units of variance are the square of the original units, which is a limitation we'll address shortly when we discuss standard deviation. In practice, there's a much easier way to calculate variance that avoids the need to compute deviations from the mean. This is the alternative formula. Variance equals the expected value of x squared minus the square of the expected value of x. In symbols, d of x equals e of x squared minus the square of e of x. Here, e of x squared is the sum of x sub I squared times p sub I. This formula is derived algebraically from the definition, but more importantly, it's much simpler to use in calculations. Instead of finding the mean, then subtracting it from each value, then squaring each difference, and then averaging sums, which can be tedious, we just need to compute two quantities, e of x and e of x squared. Then we simply square the first and subtract it from the second. This alternative formula is almost always the one you'll use in practice, and it's particularly useful when you have many possible values or when you're working with theoretical distributions. Variance has several important properties that make it mathematically convenient to work with. First, variance is always non-negative. This makes sense because we're averaging squared quantities, and squared quantities are always positive or zero. Second, the variance of a constant is zero. If a random variable always takes the same value, there is no spread at all. Third, adding a constant to a random variable does not change its variance. If you shift all values by the same amount, the spread around the new mean remains exactly the same. Fourth, multiplying a random variable by a constant multiplies the variance by the square of that constant. This is crucial to remember. Variance scales by the square. Finally, for a general linear transformation ax plus b, the variance is a squared times the variance of x. These properties are very useful when we transform random variables, and they help us understand how variance behaves under different operations. Now let's introduce the standard deviation, which is simply the positive square root of the variance. It's denoted by the Greek letter sigma. While variance is a very useful mathematical quantity, it has a significant drawback. It's measured in squared units. If x is measured in meters, variance is in square meters. This makes variance difficult to interpret intuitively. The standard deviation solves this problem because it's in the same units as the original data. If x is in meters, the standard deviation is in meters. This is much more natural to understand. The standard deviation tells us the typical or average distance of values from the mean. For example, if the mean is 10 and the standard deviation is 2, we can say that typical values are about 2 units away from the mean. This is much more meaningful than saying the variance is 4 square units. In practice, standard deviation is the preferred measure for communication and interpretation. Let's work through a complete example step by step. We'll use our familiar defective items problem. A factory produces items with defect probability 0.1. We randomly select 3 items, and x is the number of defective items. The distribution is probability of 0 defectives is 0.729, of 1 is 0.243, of 2 is 0.027, and of 3 is 0.001. Our goal is to find the variance and standard deviation of x. Step 1. Calculate the expected value, which we already know is 0.3. This is the mean. Step 2. Calculate e of x squared. This is 0 squared times 0.729 plus 1 squared times 0.243 plus 2 squared times 0.027 plus 3 squared times 0.001. 0 squared times 0.729 is 0. 1 squared times 0.243 is 0.243. 2 squared is 4 times 0.027 is 0.108. 3 squared is 9 times 0.001 is 0.009. Adding these gives us 0.360. Step 3. Apply the alternative formula. Variance equals e of x squared minus the square of e of x. So it's 0.360 minus 0.3 squared. 0.3 squared is 0.09. So variance is 0.360 minus 0.09, which equals 0.270. Step 4. calculate the standard deviation. The standard deviation is the square root of 0.270, which is approximately 0.520. So we have variance 0.270 and standard deviation approximately 0.52. This tells us that the typical number of defective items in a sample of 3 is about 0.3, and values typically deviate from this mean by about 0.52 items. Now let's look at a comparative example that clearly demonstrates the importance of variance. Consider two distributions, A and B. Distribution A takes values 0, 10, and 20 with probabilities 0.2, 0.6, and 0.2. Distribution B takes values 8, 10, and 12 with the same probabilities, 0.2, 0.6, and 0.2. Let's calculate the mean for each. For A, the mean is 0 times 0.2 plus 10 times 0.6 plus 20 times 0.2, which equals 0 plus 6 plus 4, giving us 10. For B, the mean is 8 times 0.2 plus 10 times 0.6 plus 12 times 0.2, which is 1.6 plus 6 plus 2.4, also giving us 10. So both have the same mean of 10. But what about variance? For A, E of x squared is 0 squared times 0.2 plus 10 squared times 0.6 plus 20 squared times 0.2, which is 0 plus 60 plus 80, equaling 140. Variance is 140 minus 10 squared, which is 140 minus 100, giving 40. The standard deviation is the square root of 40, approximately 6.32. For B, E of x squared is 8 squared times 0.2 plus 10 squared times 0.6 plus 12 squared times 0.2, which is 12.8 plus 60 plus 28.8, equaling 101.6. Variance is 101.6 minus 100, giving 1.6. The standard deviation is the square root of 1.6, approximately 1.26, so both distributions have the same mean of 10, but A has much higher variance. In A, values can be as far as 10 units away from the mean. In B, values are clustered very closely around 10. This is a powerful example showing that expectation alone is insufficient. We absolutely need variance to understand the full picture. So what does variance actually tell us in practical terms? Let me summarize the interpretation. A small variance means that values are clustered closely around the mean. The distribution is tight, there's little variation, and outcomes are highly predictable. A large variance means that values are spread widely around the mean. There's high variation, outcomes are less predictable, and there's more uncertainty. Zero variance means all values are identical. There is no randomness at all. These concepts have very practical applications. In finance, low variance means low risk. Investors often face a trade-off. They want high expected returns but low variance. A portfolio with high variance is risky. In quality control, low variance means consistent product quality. If a manufacturing process has low variance, the products are all very similar and meet specifications. High variance means inconsistent quality. In scientific measurements, low variance means high precision. If you measure the same quantity multiple times and get very similar results, the variance is small. The key point I want you to remember is that expectation tells us the center and variance tells us the spread. Both are absolutely essential for a complete description of any random variable. Without both, you only have half the story. Let me summarize everything we've learned today. Variance or dispersion measures the average squared deviation of values from the mean. It quantifies how spread out a distribution is. We have two formulas, the definitional formula and the much easier alternative formula. The standard deviation is the positive square root of the variance and is in the original units, making it more interpretable. Variance has several key properties. It's always non-negative. The variance of a constant is 0. Adding a constant doesn't change variance, and multiplying by a constant scales variance by the square of that constant. Most importantly, remember the interpretation. Small variance means values are close to the mean. Large variance means values are spread far from the mean. So the key takeaway is this: mathematical expectation gives us the center of a distribution, but variance gives us the spread. To fully understand any random variable, you absolutely need both measures. They complement each other and together provide a complete picture of a random variable's behavior. That concludes our lecture on the dispersion of a discrete random variable. Thank you very much for your attention. I hope this material is now clear and you understand the importance of measuring spread. If you have any questions, please don't hesitate to ask. In our next lecture, we'll explore the binomial distribution and its properties in detail. See you then.